In this section, we want to learn about vectors in 2 dimensions. 2 dimensions means planes. And we will also discuss the application of vectors. Vector is a line segment with a direction and a magnitude. It has initial point and the terminal point. Let's say P is the initial point and Q is a terminal point. Then vector point toward the terminal point that is denoted with arrow. Line segment has a length. Length is magnitude. Here is the notation of a vector. Usually, when we denote the vector, we use alphabetical character, but usually we use a bold character. Sometimes we denote the vector with the initial point and the terminal point. To clarify that indicate the vector, we put arrow sign on the top. So that is initial point. The first character is an initial point, and the next point is the terminal point. The notion of magnitude will be denoted with the absolute value sign. Absolute value sign of the vector is the length of the vector. There is a notion of zero vector. Zero vector is a vector with magnitude zero. That means zero vector is just a point. The notation will be bold letter of 0. When we discuss vectors, we discuss the direction and magnitude. So if 2 vectors have the same magnitude and direction, then we regard those vectors are the same. If you look at V and W, then those are parallel and the length of the line segments are the same. In that case, we just say those 2 vectors are the same vectors and denote like this with equality sign. But those equivalent vectors can be located in different places in a plane. We can multiply a number to the given vector. When we multiply a number to the vector, that multiplied number is called a scalar. When we have a vector v, if we multiply by -1, then it doesn't change the length of the vector, but it changes the direction. To simplify the notation, we just put minus in front of v. That means the vector with the same length with v, but different direction. Let's suppose that we multiply by 2 to the given vector, then that vector will be twice bigger than the original vector, but it doesn't change the direction. So that is the vector with the same direction with twice bigger length. This time we multiply by -2 to the vector v. If we think about the absolute value of -2, then that is 2. That is associated with the length. That indicate that the new vector is twice as large as the original vector v, and negative number indicate that the vector is in an opposite direction. We can add two vectors. Let's say we have a vector v and a vector u and vector v. Then what we do is we draw the parallelogram, and then we connect this initial point with the tip of the vector u. This is u plus v. We want to consider the difference of two vectors, u minus v. Then we can consider this as u plus -1 times v. So indeed, we have the vector u and vector v, and u stays the same, but v, we consider adding two vectors u and -v. So we have to connect the initial point of u and the terminal point of -v. See here, when two vectors are added, you start at the initial side of one of the vectors, and then you will end at the terminal side of the other vector. You can look at these two combinations, and you can look at these two combinations. You will see the same thing. So we apply that principle when we think about u minus v. We start at one vector and we end at the other vector. We can locate the vectors in the coordinate plane and denote those with a coordinate form. We have a vector p to q. Let's say this vector is v. Then we can denote that vector in a coordinate form by using something similar to arrow notation. Those will have two components. The first component is about horizontal component. The next component is about vertical component. When we describe the horizontal component of the vector, we think about the horizontal difference. So x2 minus x1. And the vertical component will be y2 minus y1. Of course, the p as a coordinate, that is x1 and y1. Q as a coordinate, that is x2 and y2. It is similar to the subtraction from the terminal point to the initial point. That is called component form of a vector V. What you have to be careful is the notation. We are using the arrow notation. If you use parentheses, then it'll be just a coordinate. That is not a vector. Let's do some example. We want to find the component form of the vector with initial point -1 and 5 and terminal point 2 and 3. So this point is a terminal point. This point is a initial point. So arrow goes this direction. And when we consider the the component form, we think about terminal point minus initial point. So this is a terminal point, so it comes out first, and 2 minus the initial point of the x coordinate. And then again, the terminal point 3 minus initial point, which is 5. So that'll be 3 and minus 2. In this problem, the vector is given and initial point is given. What we want to do is we want to sketch the vector 2 and -3, which start at 0, 0 and 2, 4. Horizontal component of the vector is 2. That means we move to the right two units from the initial point, and -3 means we go down 3 units from the initial point. So when W equals 2n minus 3, and when the initial point is 2 and 4, the terminal point will be 2 plus 2 and 4 minus 3. So terminal point will be 4, 4 and 1. So this is the terminal point. And vector looks like this. If we start at 0 and 0, we go through the same process. So W is 2n minus 3, and terminal point will be 0 plus 2 and 0 minus 3. So that is 2n minus 3. This is, indeed, this should be the coordinate. So this is the terminal point. When we have a vector whose component form is A1 and A2 on the plane, we can calculate the magnitude of the vector by using Pythagorean formula. Here the horizontal length of the vector is A1 and the vertical length of the vector is A2. So if we just apply the Pythagorean formula, then the magnitude of the vector is square root of A1 squared plus A2 squared. In this problem, the vector is located on the plane and the initial point and terminal points are given. And we have to figure out what the component form of this vector is, and then we have to calculate the magnitude of the vector v. In this picture, P is the initial point, and Q is the terminal point. So the component form of the vector will be calculated from terminal point minus initial point. Component-wise, we have to use this arrow notation. The terminal point is minus 1. The initial point is 2, so minus 2. And terminal point is minus 2, and the initial point is 2, so minus 2. So we get the component form of the vector expression minus 3 and minus 4. Magnitude of the vector can be calculated by looking at the triangle or just looking at the component form of the vector. It is enough to think about just the absolute value of those two values, because if we think about the distance between this point and this point, then that is 3. The distance between these 2 points is 4. So we will use that notation, just the dot length. So by applying the Pythagorean formula, we have square root of 3 squared plus 4 squared to get this hypotenuse. So that is square root of 9 plus 16, which is square root of 25. That is 5. We thought about the right triangle, but indeed we calculated the length of the vector, so that is the magnitude of the vector. So far, we learned about how to express the vector in a component form. When we express the vectors with component forms, we can add, subtract 2 vectors. We can think about the algebraic operations on vectors. Let's suppose that U is A1 and A2 and V is B1 and B2. Then when we add 2 vectors, we just add those component-wise. X coordinates will be added together and y coordinate will be added together to form the vertical component, and do the same u minus v, a1 minus b1, and a2 minus b2. We can also multiply the real number to the vector. Here c is a real number. Then we multiply c to the horizontal and vertical component, c times a1 and c times a2. When c's are, we already know that that is called a scalar. Let's suppose that the vector u is 1 and negative 2, and the vector v is 3 and 5. We want to find negative 2u. I said we have to multiply that number to each component. Then we get minus 2 and 4. In the next problem, we will think about u minus v. Then we do component-wise. U is 1, x component, the horizontal component is 1, and the horizontal component for v is 3, so we subtract it. Do the same, minus 2, minus 5, then that is minus 2 and minus 7. In the third problem, we think about u plus 3v. U was 1 and minus 2, plus 3 is multiplied to v. V was 3 and 5. Then that is 1 and minus 2, plus we do a kind of distribution. We apply the scalar multiplication to each component. So that'll be 9 and 15. Then we will add component-wise. Then 1 plus 9 is 10, and minus 2 plus 15 is 13. So that is the coordinate. We define the algebraic operation among vectors, so we can discuss the properties of vectors. If we add two vectors, then we can switch the order of operation. So u plus v equals v plus u. U plus v plus w can be calculated as open parenthesis u plus v close parenthesis plus w. This was associative law. And obviously, if we add a zero vector to the vector, then that'll be vector itself. There is an inverse property. If you add minus u to u, then you will get a zero vector. We also learned about scalar multiplication of the vector. If we think about the length of that vector, then that equals the absolute value of c times the length of u. The next one is about multiplication by a scalar. C is a scalar, and we have vector v and u. Those are added. Then we can distribute it. That equals c times u plus c times v. We have two scalars, c and d, and we have a vector u here. Then again, we can do distribution with a vector. Then it becomes c times u plus d times u. Here c and d are scalars, so real numbers. We have scalars 2 are multiplied, and then we multiply that to the vector u. Then that is the same as c times d times u, and also the same as d times c times u. All of them are pretty obvious. If we multiply the scalar, which is 1, to u, then that is the vector itself. If we multiply by 0, 0 is a real number, times u, then that will become a 0 vector. This is a scalar. This is a vector. And we have any real number, and we multiply that to the 0 vector, then that'll be 0 vector. A vector of length 1 is called a unit vector. In the following problem, we want to determine whether the given vector is a unit vector or not. The first vector is 3 over 5 and 4 over 5. Unit vector is about the length of the vector, so we have to figure out the magnitude of the given vector. We use the Pythagorean formula to do that. We will think about 3 over 5 squared plus 4 over 5 squared. Then that'll be 9 over 25 plus 16 over 25. So that is a 25 over square root of 25 over square root of 25. That is square root of 1, which is 1. So we can say that that is a unit vector. In the next problem, that is 1 over 2 and 3 over 5. Again, we will think about the lengths 1 over 2 and 3 over 5. Then we apply the Pythagorean formula. Then that'll be 1 over 2 squared plus 3 over 5 squared. So that'll be 1 over 4 plus 9 over 25. We have to think about the common denominator. Let's just go with 100 because that is easier. So that is, the first one is 25 over 100 plus, we have to multiply 4 on the numerator and denominator, then that'll be 36 over 100. So that is square root of 61 over 100. That is not equal to 1, so that is not a unit vector. There is another way to denote the vector. We can use I and j. When you use I in vector, that represent 1 and 0, horizontal unit vector, and j is the vertical unit vector, 0 and 1. We have a vector a1 and a2. We can use those horizontal unit vector and vertical unit vector. This is a horizontal component and this is a vertical component. So we can regard that as a scalar a1 times horizontal component I plus scalar a2 times vertical component j. That is another way to denote the vector. In the next problem, we want to convert the component form of the vector into the vector using I and j. So vector u is minus 8 and 6. Then the horizontal component is minus 8, so minus 8i plus vertical component 6 times j. If we have a vector u which is denoted as 10 and 0 in component form, u can be written as 10i plus 0j, but 0 times 0, j is just a 0, so we can just write down 10i. The next example is finding 4 times u and 3u minus 2v for the given vectors. U equals I plus j and v equals I minus j. It is nothing but just an algebraic operation. 4 times u was given as I plus j. Then we do distribution. Then we have 4i plus 4j. We know that is 4 times 1, 0 plus 4 times 0, 1. So this is the horizontal component. This is the vertical component. So that becomes 4 and 4. The next one is 3u minus 2v. That is 3 times u is I plus j minus 2 times v is I minus j. We just do common calculation, then that is 3i plus 3j minus 2i plus 2j. So those two will be combined and those two will be combined like terms. 3 minus 2 will make I, and 3 plus 2 will make 5j. This is 1 times I, so horizontal component is 1 and vertical component is 5. So this is the final answer. Let's suppose that we have a vector on the plane. The direction of the vector v is the angle between the positive x-axis and the vector. When the angle is the direction of the given vector v, that angle is the smallest positive angle in standard position. When we know the direction of v, we can figure out the horizontal component and vertical component by combining with the length of the vector. So by using the direction of the vector v can be written as the magnitude times cosine of theta I plus magnitude of v times sine of theta j. In this problem, the magnitude of the vector is given. The magnitude of the vector is 32, and theta, which is the direction of v, is 30 degrees. We want to figure out the horizontal component and vertical component, and then we want to write the vector in terms of I and j. Let's figure out the horizontal component. Horizontal component was the magnitude of the vector times cosine of the direction of the vector. That is, v was 32, and cosine of 30 degrees is square root of 3 over 2. So we get 16 square root of 3. Vertical component of the vector is v times sine of the direction vector, which is 30 degrees. The magnitude was 32, and sine of 30 degrees is 1 over 2. Half of 32 is 16. So horizontal and vertical components are given, so we can finally express the vector with I and j. 16 square root of 3, which is a horizontal component, so we attach with I, plus 16 was the vertical component, so we attach with j. In this problem, the vector v is given, and we want to think about the magnitude and direction of the vector. For the magnitude of the vector, we will use the Pythagorean formula. So we think about minus square root of 2 over 5 squared plus minus square root of 2 over 5 squared. Indeed, we don't have to think about this minus because we are thinking about the length, but it doesn't matter. That is 2 over 25 plus 2 over 25. So that becomes square root of 4 over 25. If we simplify, then that is 2 over 5. Now we want to get the direction. We will use tangent because we know x and y value. If we locate that the terminal point of the vector on the plane, then that'll be in the third quadrant. So we are thinking about this vector. The first thing we want to do is we want to figure out the reference angle theta prime. We think about tangent of theta prime, then that was defined as y over x. Y is minus square root of 2 over 5, and x is also minus square root of 2 over 5. Those are the same, so the fraction will be reduced to 1. So we know that tangent of theta prime equals 1, that is 1 over 1, that is 45, 45, 90-degree triangle. So the reference angle theta prime equals 45 degree. Now we have to calculate this angle. We know that theta prime is 45 degree and this is 180 degree. So when we add them up, we will get 225 degree. So theta equals 180 degree plus 45 degree. That is 225 degree. So that is the direction of the vector. The last problem of this section is a real-life application problem. Once you figure out the geometric circumstance of the problem, then the problem can be easily solved. In this problem, a man is pushing the object parallel to this surface, and the force is 32 pounds. That is the magnitude of this vector. And then we have to figure out the horizontal and vertical component of the force. If we draw the right triangle here, then this elevation is 30 degree, so this angle is 30 degree. And what we have to think about is this force and this force. This 32, the magnitude of the vector, is the hypotenuse of the right triangle. So horizontal component of the vector is 32, cosine of 30 degree. So that is 32 times square root of 3 over 2, which can be reduced to 16 square root of 3. And vertical component is, in the picture, the force is toward the ground, which means the vertical direction is negative, so we will put minus here. And then 32 times sine of 30 degree, so that is minus 32 times 1 over 2, which is minus 16. to repeat the argument, if we just think about the triangle here, this is 30 degrees, and this length is 32. We essentially try to figure out the length of the vertical line segment and the horizontal line segment. If this is B and if this is A, then what I used was cosine of 30 degrees equals adjacent over hypotenuse. So adjacent is A over hypotenuse is 32. So A is 32 times cosine of 30 degrees, and A is a horizontal component. We can calculate B, which is a vertical component. Similarly, we start with sine of 30 degrees, then sine is opposite, which is B over hypotenuse 32. So B is 32 times sine of 30 degrees. That's what is written here. If we write the vector in terms of I and j, then that'll be 16 square root of 3i minus 16j.